Okay, so lesson 7, global resource management concept. In this lesson, we will learn how to manage resources in the clustered environment. So that will include Anchor resource management and global cache resource management. So we will discuss two different topics. And this lesson, I will review in a few slides by reading each bullet, and also I will get into a class note to discuss further. So I will deliver this content slightly different from the other lessons. After completing this lesson, you should be able to describe the need for global concurrency control. So here, the keyword is concurrency, and another keyword is global. So how do you control concurrency? That's the important part. And also, we will have to know what is a global resource directory and how global resources are managed, and RAC, global resource access coordination. And these are topics in this lesson. And need for global concurrency control. I'm going to read each bullet, and then when needed, I will use a class note to discuss further. First bullet, Oracle requires concurrency control because it is a multi-user system. And single instance Oracle provides concurrency control by going through latches and mutex for memory structures, and enqueues for resource control, and buffer cache pins for cache management. In RAG environment, and structures and resources may be accessed by or modified by a session running on any database instance. Thus, a RAG environment also requires global concurrency control. So we use global locks and also global enqueues and also global cache fusion to control library and raw cache access, and to control resource access, and also to control buffer cache access. Okay, so let's get into this area. Okay, so I'm going to actually discuss this topic. So this diagram is giving you a concept of a locking and concept of a concurrency. Sometimes you may be confused, locking as a concurrency and concurrency as a locking, something like that. I made one very simple example here is, and in this particular example, I have this example. And this is my database block here. And the block consists of a header and reserved free space to support update statement. And also, we have the data section. So your data is stored in the data section. In this example, session 1 at time t1 issued the update statement. So I want to update row number 10 in the given database block. So if that is case, if session 1 request update statement, then row 10 will be handled by session 1. And in order to actually support this update statement, what happened is behind the scene, we will have to allocate transaction slot to store lock status information. So the row level locking. Okay. So session 1 is a current session 1 currently updating row 10. So this row 10 status row 10 is being used by session 1 for DML. So that information is saved in the data block header by going through transaction slot. So allocate a small slot and then save a status of a row until transaction is complete. At this time, just right after, session 2 requested the same row for another update. Now this time, session 2 will access to database block, but this row is being updated but not committed yet. So session 2 cannot access to this row because of this locking mechanism. Now what if at session 3 issued a delete statement to delete same row? Then what will happen? Yeah, same thing. Row is locked and status information saved in the block header, so session is blocked. So as you can see, by keeping row status information in the block header, we can easily lock sessions until transaction is complete. At a later point, let's say we have this. Session 1 committed transaction. So now we have session 2 and session 3, and these two sessions can access to row number 10. So which session must be served first, session 2 or session 3? I know initially session 1 requested a row for update statement, so there was a locking mechanism that is blocking other sessions, okay? Because a block header indicated status of a row, but you commit session 1 committed. Then what? So which session must be served first? From this example, I can say session 2. Does the Oracle know about this? In this example, no. So we have a concurrent request, and which request must be served next, and first or next. So we need additional mechanism to control concurrent request. That's a concurrency mechanism, in addition to locking mechanism. Okay. So in this example, it doesn't show which session must be served first and which session must be served next. But behind the scene, we use enqueue mechanism. For example, when session 1 requested row for transaction, behind the scene, we had to acquire transaction log and also share the table log. So enqueue is assigned for this transaction. So if a session 2 requests same row for update statement for DML, then session 2 must be enqueued. Okay, so we have a session 2 in the transaction log transaction enqueue, and also session 2 request is placed in the shared table enqueue. And also when session 3 requests same row for delete statement, but TX TM log is held by session 1, so session 3 request must be enqueued in the TX and the TM log as well. So we will have another session request, session 3, and also we have another session request, session 3. So in the TX enqueue and TM enqueue, we have two requests are saved. So once session 1 complete transaction, then based on first in, first out algorithm, so in this case, we have first in, first out in algorithm. Session 2 is served next. And when session 2 complete its operation, and then session 3 will be served. So that's a simple example. So in addition to lock, we need also a concurrency mechanism. If this were RAG environment, then let's say session 1 requested transaction log and shared the table log from local instance 1. And also we have a session 2 coming from remote instance. And also request the same role for another update statement or delete statement. Then those session requests must be enqueued. And then those requests must be served based on first in, first out to control concurrency. So that is actually a concurrency mechanism. And this concurrency mechanism is used not only a single instance database, but also RAG embodiment. And this mechanism is used globally. So global resource, global concurrency mechanism is used. I have another example. The other example here is, so I have actually a memory structure. And we have a shared pool, and we have a buffer cache, and we have a local buffer. So we have different memory structures. And you probably heard about latches and mutex. For example, to protect shared pool component, we use a shared pool latch to control memory allocation and deallocation, and library cache latch for the lookup and search operation, and also row cache latch, and so on. And also to control the blocks in the buffer, we also use a buffer chain latch. And also to protect data in the local buffer, we use a redo allocation latch kind of things. Okay, so in order to control access to the data in the shared pool, data in the buffer cache, data in the local buffer, and data in the other memory area, okay, we will have to have a way to control concurrency. Okay, think about that. You have one session, and one session issues a SQL statement, and they require the index scan. So my SQL statement and index scan information saved in the shared pool, especially library cache, for example. And also we have a session 2 and session 3. These two sessions issued two different SQL statements at the same time. And one session, session 2, it does request save the execution plan to use index scan. And third session issue the drop index command at the same time. And what will happen? Okay, so does the session give up index scan because of a drop index command, or does the index scan the drop index command must wait until the index scan is initiated? So that's what we have to control. If this were a RAG embodiment, same thing. In instance 1, we issue the SQL statement that requires index scan. At the same time, in a second session, issue the drop index command. What will happen? Okay, so this kind of a concurrency must be controlled. So in RAG embodiment, the library cache and also memory cache access are controlled, okay, by using concurrency mechanism. And also buffer cache. So here we have in the single instance embodiment, the buffers are managed by using its own buffer access mode. So it has a buffer access mode pinned or free, which is unpinned. And also buffer state, unused and clean and dirty, and also buffer mode, current and consistent. And these are a way to manage the data blocks in the buffer. In the clustered environment, we will also have to use same or similar buffer state or buffer access mode and buffer the mode to be able to manage a consistent image of a cluster by controlling concurrency. So that is one thing what we have to understand. So just like a single instance database, we have to have a way to control the access to the shared resource and access to the resources. Okay, so let's take a look at global resource directory. An object under global concurrency control is called a resource. And resource metadata is held in the global resource directory. global NQ resources are used for NQs and locks. And also global cache resources are used for buffer cache control, which means that global resource directory, it keeps metadata to manage NQ, the resources, and also to manage cache resources. And where is the location of a global resource directory? The location is the shared pool location in each instance. And each currently managed global resource directory resource has a master metadata structure and one or more shadow metadata structure, which means that each instance can have a master metadata, which means that a master instance can modify master metadata in the global resource directory to manage global NQ resources and to manage global cache resources. And also, another instance also can have their own the master metadata as well. So a master instance can modify master metadata. And it's part of global, the global resource directory is a part of a shared pool. And we have also some more information here. Global resource management. After first access of a globally managed entity by any instance, a global resource is allocated. And it is used in our internal algorithm. So, to manage a global resource, the metadata is generated, and metadata can be master metadata to specific instance or shadow metadata. So based on the assignment of master metadata and also shadow metadata, that's internally controlled. And the instance they can modify in a metadata that is called master instance for that specific metadata. And also subsequent access to an entity from another instance for which resource master metadata exists causes resource shadow metadata to be allocated in the requesting instance and update to be done to the master metadata. So it's just so confused, right? It's very confusing part. Suppose that instance 1 requested a resource and the metadata populated, and based on internal algorithm, instance 1 became master instance for that particular metadata. So if instance 2 requests same resource, but now that metadata of a requested metadata and also requested resource is owned by instance 1, then instance 2, requesting instance, always ask master instance to update the metadata. And then master instance will copy the metadata as a shadow metadata, so that way instance 2 can take action. And global resource mastering. Remastering is the process of allocating control of master metadata for specific entity to another instance. So for example, we have an object with 100 blocks, for example. And as time goes on, Oracle assigned the ownership of those blocks, and pretty much evenly. For example, we have a 2-node rack database, and instance 1 has metadata to control 50% of the blocks. So instance 1 is a master instance for 50% of the blocks on object. And second instance is also master instance for the rest of 50% of a database blocks of an object. Okay, so the ownership of a resource is evenly distributed. Now, if there is an instance failure, for example, then this ownership of a resource must be redistributed. And that is in instance level or lazy remastering. Or when you start up database instance, and that's in another case where resource remastering occurs. And also we have a file level affinity remastering, meaning that if one of the instances access to the blocks of a data file more frequently and more time, then the ownership of entire blocks for that specific file will get changed. So at the file level, that's in a file affinity. But sometimes they're changing ownership of blocks in the entire data file. That may be too much. So that's why starting from Oracle Database 10.2, we also can use object affinity, which means that if in the given time, if one of the instances access to object more frequently based on internal condition, then the entire blocks of object will be remastered. So one of the instances can have the ownership of those blocks. And also in 12.2, resource mastering is further optimized using service-oriented buffer cache access, which means that starting with 12.2, the ownership of a resource is distributed only based on instance where service is running. So if you have the sessions that are connecting through a service, and service is running through 2 instances out of a 5-node rack database, for example, then only through instances where service is running and resource, the ownership will be distributed. So that is another optimal way to manage the resources and ownership. And global resource recovery. When one or more, but not all instances fail, then failing instance resource masters are lost. Now it's exactly the same as the instance recovery scenario. If one instance goes down, what was the first step? Recovering global resource directory information. So the metadata in the global resource directory must be redistributed. Okay? So that will be done behind the scene before actual block recovery. Surviving instances can rebuild resource master metadata for a specific resource by aggregating details from surviving shadow metadata for the same resource. And global locks and enqueue metadata are done first and followed by global cache metadata. The rebuild results in each surviving instance mastering some of the recovered resource master metadata. Processes, and these are global resource global resource related background processes. And we're going to actually take a look at this now. So up to this point, we learned this point. So we have actually a global resource directory. This is actually the directory that stores metadata. And this metadata is for global enqueue management and also global buffer cache management. I want to manage latches globally. I want to manage mutex globally. Or I want to manage enqueues globally. I want to manage buffer state globally. Okay? And the global enqueue management is also divided. One is to manage enqueues globally. Okay? For example, and transaction enqueue, and also share the table enqueue, and also sequence related enqueue, and undo related enqueue. I want to manage enqueue globally. And also global instance locks, library cache access and raw cache access. I want to manage this information globally. Okay, so all this information saved in the global resource directory. So where is the location of a global resource directory? The location is shared pool. So same information saved in this location, shared pool, and also in this location. And this the location is accessed by global enqueue service background process and global the enqueue service in the background processes as well. So let's make it one simple example here based on that. Okay. So I read in a few texts, and it was a little bit difficult to understand. Okay, because of a terminology confusion and concept confusion. So this example will give you a little better idea. So in this example, this is two-node rack database, ORCL1, ORCL2. And we have a global resource directory. It includes metadata for global enqueue service and metadata for global cache service. Okay? And when we look in a global resource directory, we have this information. And this is a part of it. And this the node is giving you metadata information on global cache service. And there is a global enqueue service metadata as well. I just made it one simple example. So suppose that I have one segment that consists of 4 blocks. I made it. I oversimplified this example, and the block number is 10, 11, 12, 13. 4 blocks. When first instance access to the resource, which is an object, and the ownership is distributed. For example, block number 10 and 11, and its metadata can be modified by instance 1, for example. So I have a block number 10 and 11, and each master is an ORCL1 instance. And also, blue color 12 and 13, each owned by instance 2, meaning that metadata can be modified by second instance. So when you're looking at global cache service metadata, it's identical. But what's different is the metadata ownership is different. The first 2 entries are owned by ORCL1. The second 2 entries owned by second instance. So based on internal algorithm, metadata entry ownership evenly distributed. We have a session 1, and session 1 connected to instance 1. And what session 1 want to do is, session 1 request block number 12 for update statement, for example. Okay? Now, at this point, when you look at this, the buffer state is a null, meaning that blocks are not in memory yet. Or buffer state is a null. There is nothing going on here. So session 1 requested block number 12. Can I just cache this database block? But how do I know this block owned by instance 1? Thus, instance 1 can modify metadata to cache this database block for DML. So foreground process doesn't know about this. What session 1 has to do is, session 1 must request global cache service background process. That's LMS process. And then we ask LMS process to check global resource directory to see who is owner of this block. So I'm in the instance 1. According to this, block number 12 owned by instance 2. So what LMS does, it will send a message to remote LMS process and ask remote LMS to update global resource directory metadata and then return it to requesting instance. So what it does, so let's check what is the status. Okay, I'm the owner, and according to this buffer state, it's a null, meaning that block is not in memory. So the LMS process in the second instance, it will update status of this block. Let's say I want to actually change it to exclusive lock in the first instance, for example, meaning that I want to update this buffer state and this metadata to let session 1 cache database block for DML, so exclusive buffer state. And this updated information is copied, so 12 and ORCL2 and also exclusive lock. And this metadata, shadow metadata, is sent back to the requesting LMS process. So it will save this information and update this information, and then eventually notify session 1. So session 1 received this message, so now I'm able to cache this database block into local instance, requesting instance. As you can see, we change messages to keep consistent image. Okay, think about that. You actually cache the block for DML, but session 2 doesn't know about that. And session 2 also requests the same block for another transaction. Then it's easy to make a data divergence issue. That's why at NIST, small messages must be transferred, okay, to maintain same and consistent information and to keep integrity of a cluster. And this example is to maintain global cache service metadata and global cache service resource. And LMS, it is a background process that is working for global cache service. Okay, so let's come back here. And global resource access coordination, just like global cache service metadata management, as a part of a global enqueue management, we also manage metadata for global enqueue, global instance locks, in addition to global buffer cache. And when you look at a global enqueue management, so it's very similar to my example that I showed you. Suppose that session 1 is requesting global enqueue. And here we have one background process, LMD background process. And this is a global enqueue service background process. So when a user requests the global enqueue, then LMD process in the requesting instance, it checks the ownership of a resource. And when needed, LMD locate master instance and forward the message to masking instance. So a master instance will manage metadata and update metadata and then send the updated information to local LMD, and local LMD will update local information accordingly and then notify session about this change. So this is about global enqueue resource management. So it's pretty much the same as this. You can just replace this with LMD and also LMD. But this time it's not global cache service management, but that's global enqueue resource management. And also we do have instance lock management. So we want to manage instance lock on raw cache entries and library cache entries and reserve cache entries. And this instance lock management is done by another process, in this case, LCK process. Okay, so LCK process will manage metadata to protect the raw cache and library cache and reserve cache globally. Okay, so this is actually our example. So based on that, let's come back here, and then let's go through again. And we had actually this discussion, and locking and concurrency is different. So we lock a resource to protect the resource that is currently being processed by a session. But we also need a concurrency. Once lock is released, and we have to know which session must be served next, and then which session must be served first. That must be controlled. That's the concurrency mechanism. And also, resource in the shared pool must be maintained and managed, and concurrency to the buffers in the buffer cache also must be maintained, and same thing in other memory components. And then we discussed about global resource directory, and also global enqueue management, and global buffer cache management metadata. It is saved in the global resource directory in the shared pool. And also we had a discussion of global resource directory and global resource metadata management by going through LMS process and global cache service example. And also in the slide, we had an example of global enqueue service example and LCK process in an example. So one thing what we learned here is in RAG embodiment, we have to keep consistent information. So that way we can avoid the data divergence, and we keep the RAG database integrity. And for that matter, we use global resource management, and then that is very important. That's why every time when you restart, if you have an instance a failure, for example, and global resource metadata always recovered first, because that's very important the information. So up to this point, I briefly introduced an overview of a global resource management. In the next part of this lesson, what I'm going to do is I will get into global cache management more detail, and there are more examples available. So by reviewing few examples and scenarios, we will have time to learn more about global cache management. And this is the first part of lesson 7.